Hello, Physics 20s. I wanted to go through a couple of the Kepler's laws practice questions. Again, I want to encourage you to be patient and to get comfortable entering big numbers into your calculator, and I'll walk you through a little bit of that right now. The first question I want to focus on is number 3. It says, if a satellite's to orbit the Earth at that altitude, what would its orbital period be? Now, I'm going to actually try and do some of this work right here. So, it would be really nice. Well, actually, the first thing we need to recognize is that if the Earth is, or if we are 1,000 kilometers away from the Earth, okay, so we're out here somewhere, okay, and the altitude is just the distance from the surface of the Earth out. I'm going to turn this into meters right away because we're going to need meters, and you'll find that for almost all of our math that we need to use meters. So a shortcut is you have to take 1,000 kilometers and times it by 1,000 to get it into meters. One way you can do that with exponents is just add 3 to the power, because it's 3 powers of 10 or 1,000. So then this distance here, it's really 1e, or 1 times 10 to the 6th meters. And that's the distance out. So some of you are probably catching this from my horrible drawing here, that what we need to do is we need to add the radius of the Earth to that altitude, because we need the total separation distance, which is r. Okay, now it's easy to think that r is always a radius. Well, it is a radius, but it's from the center of the Earth to where the astronaut is. Okay, so we're going to need to add the distance of the Earth, or the radius of the Earth, sorry, which this is horribly disproportionate. I'm sorry about that, but it's really 6.38 times 10 to the 6th meters. Okay, that's off your formula sheet. So it means then that r, the total distance, is actually going to be those two added together, 7.38 times 10 to the 6th. Okay, and that'll be meters, of course. Now, that's just the radius. So you have to catch all of that before we even start doing stuff, because if we're trying to find the orbital period, what would be really nice is if we knew what Kepler's constant was for the Earth, because Kepler's constant is equal to the period squared over the radius cubed. Okay, and we just figured out the radius. It's 7.38 times 10 to the 6th. But I don't know what Kepler's constant is. So this is where things kind of get a little crazy, but not really, because Kepler's constant can also be written like this. K is equal to 4 pi squared over gm1. And that is equal also to t squared over r cubed. So the power in this math is, yeah, we don't know Kepler's constant, but we do know what the mass of the Earth is. Okay, again, from your formula sheet, that's 5.97 times 10 to the 24th kilograms. Okay, so this kind of gets a little crazy, but we can manipulate all of this to solve for t. Now I'm just I'll erase all this afterwards because it's starting to get messy here. I just wanted to show you my steps. So basically, if I cross multiply, or no, if I bring r cubed over here, so I times this side by r cubed to get rid of it, and then square root both sides, because I just want t, then I get this derivation right here. So the period t will equal the square root of 4 pi squared r cubed over gm1. Okay, now that's how you find it. What you have to be really careful of, though, is that you enter this in your calculator correctly. So you go 4 times pi squared times the radius, which we found to be the 7.38 times 10 to the 6. Okay, we need that number in for the radius. And then what you have to be careful of is that you divide by the product of the denominator. Okay, so 6.67 times 10 to the negative 11 times the mass, 5.97 times 10 to the 24th kilograms. Okay, I really, really stress that EE button. Just send me a quick text or send me a quick email or something if that's you're having difficulty with your calculator on that, because it's going to save your life like crazy here for all this math. Okay, but if you do that very carefully, you should get the answer that is posted, which is it's 6.31 times 10 to the third seconds. And what's really cool is if you keep track of all your units, you're going to be left with seconds in the end. Now, there's a mess of units in there. Okay, so that is a tip for number 3. Okay, let's make room here for number 5. I want to jump to number 5. Okay, I think I got most of that. Okay, so number 5, it has basically 2 steps to it. And sometimes I joke and I call this the physics 2-step, because you have to use one formula to get a variable that you need, and then you take that to the last formula that you need. So part of this, again, just follow the basic grasp method here and identify everything that you know. And, oh, whoops, that's not what we know. The first thing we know is that this we have a satellite that has a centripetal acceleration of 3.56. So that is AC. And we also know the radius, okay? It's orbiting the planet with that radius, the 7.6 to e to the 7th meters. So if we want Kepler's constant, here's the catch again. If it helps you, just go, well, if I want to get Kepler's constant, I really need t squared over r cubed. That would be really nice. But I don't have t. So where could I get it? The clue comes from the fact that you know the centripetal acceleration. Okay, now I know these formulas are still kind of fresh, but if you look at in your formula sheet, you have 2 formulas for centripetal acceleration. AC is equal to v squared over r, or AC is equal to 4 pi squared r over t squared. Now, we have the centripetal acceleration, it gave us that, and we also have the radius. So can you see here that we could manipulate this expression and solve it for t? Now, it's a little, you have to be careful with it, but we can do it. I would multiply both sides by t squared, and then it would look like, and then divide by centripetal acceleration, so then it would look like this. T squared is equal to 4 pi squared r over AC. And if you're catching this, like you might say, well, we need to square root that. Well, I really need t squared, don't I? Because look, if I have t squared, it goes right here, and then I divide that by r cubed. Then I can get k. All right? So leave these, like carry these numbers. They're just ugly, okay? But carry them. In the end, you won't be surprised, and that's what all the answers are, that your answers are going to be in seconds squared over meters cubed, because that's exactly what the units are going into that. So I'll let you try that one as well. I think the answer is B for that one, but just see if you can get that one. Okay, and then the last one I want to hit on is number 8. I mean, there's lots of examples of all of these questions. They kind of duplicate themselves, but just be prepared for that. So number 8, as soon as you know that you are dealing with 2 objects that are orbiting a single mass, then you can use then you can compare their periods and their radii, because they should have the same Kepler's constant. Remember, those 2 satellites, or any 2 satellites, would have the same ratio of t squared over r cubed, because they're orbiting the same planet. Okay, so it looks like from this question we have 2 moons. I got Ariel and Titania, and for Ariel, we know Ariel's radius r, and we know Ariel's period t. So we could label that r, the radius of Ariel, and the period of Ariel, if you wish. And then we, orbiting Uranus, there's also another moon named Titania, and we happen to know Titania's radius. Okay, there now, so we could label this the radius of Titania. And what we don't know is we don't know the period for Titania. Okay, so the setup here would be, and I would try and just keep it the same. We'd say the period of Titania squared over the period, or sorry, the period of Ariel squared over the period of Titania squared would equal the orbital radius of Ariel cubed divided by the orbital radius of Titania cubed. Okay, so because you have three of the variables, you can cross multiply and divide. Now make sure you cube and square, okay? Otherwise it isn't going to work. Yeah, I'd probably take the radius of Ariel, times that by, or cube it, times that by the Titania's. Oh, sorry, I did that backwards. We don't know the orbital period for Titania. So this is what we're trying to find right here. Okay, so I would multiply those two, divide by that, and then make sure you square root it to get the period. So anyway, I'll post that for now. That may, hopefully that's enough for you, because I definitely want to give you a lot of time to absorb this. I think this is a fairly complex concept. The fact that you need to kind of master Kepler's constant and know that there's all the variations in terms of what you can find. But I'm confident if you go slow, and again, be patient, you could have all the right setup, but you're not closing your brackets, or you didn't get the exponents right, and or you forgot to cube root or square root. So just be very, very methodical with this analysis, and I think you'll get it.